Hi everyone, welcome to the second lecture of the third day of class this Friday. So today we are covering, in addition to 6.3, section 6.4, which is the shell method. So this is another way to solve the types of problems that we were talking about in the last lecture, right? Specifically, we're going to talk about a different method in order to figure out the volume of solids of revolution, right? So this is where we take some curve and we rotate it around one of our axes or some other line in order to get a volume, and we're trying to figure out the volume of these shapes, right? So this is another method. Now you might be asking yourself, well, why do we need another method? We already have the washer method and the disk method that we talked about in the previous class. So I'll pull up this picture right here. If you look at this picture and we're revolving around the y-axis and we're trying to figure out the radius of our washers, right? Well, we have something like our first radius is R1 right here, and while our second radius is R2. However, these are the same curve, right? We have two different radii in the same curve. So what happens is that we'll need to take the inverse of this, right? We need to get the function in terms of y instead of in terms of x, and this is not easy to do with this function. Right, so when you try to do this, it just doesn't work very well, so you don't get nice functions that you are actually able to integrate. So the shell method is a way to fix this problem by, instead of looking at these disks, we're actually going to be looking at hollow cylinders or shells instead. So this is best seen with a picture for sure. So let me pull that up right here. So in the disk method, right, what we would do is we would always have our disks being parallel to the axis that we were looking at. So in this case right here, one of our disks would have been like this top circle here, and then all filled in around it, right? However, in this case, we're actually going to be looking at these cylinders instead of the disks. And what this allows us to do is it now allows us to, instead of looking in this case as a function of y, we can instead look at it as a function of x. So if we are looking at the area of some cylinder like this, so we have a hollowed out cylinder that looks like this. So exactly this picture we're talking about before. Let's just say it has a radius of r and a height of h. We know that the surface area, or the area that we're going to be looking at, is going to be 2 pi r times h. You can think of this as if you cut the cylinder in half and unfurl it out. It's going to be a rectangle with 2 pi r on top, right? That just comes from the circumference of the circle that we have on top, and a height of h. So in this picture here, if we're looking at the area for a specific value of x, we're looking at a radius right here of this. This is our radius. Well, the radius in this case is just equal to x. And it's the distance from our y-axis, so our radius is going to be x. And our height then is just going to be our function of x, right? It's going to be how tall along the curve that we are. And so this is our height, which is going to be equal to f of x. So h equals f of x. Right, and we can use the same method we talked about last class, where we're going to add up all of these now cylinder areas instead of shell areas to get our volume of our shape. So I have another picture of that. Pull that up. So you can kind of think of it similar to the Riemann integrals where we would take these rectangles, make them smaller and smaller and smaller to approximate integrals. We can just do this for these problems where we have these shells, these cylinders. We make them smaller and smaller and smaller until we actually get the volume that we are looking at. So in particular, let's talk about first revolving around the y-axis. That's the easier case, revolving around y-axis. We're going to have the integral from a to b of 2 pi x f of x dx, where a is going to be the leftmost x value, and b is the rightmost x value. B is the and this 2 pi x f of x just comes from plugging in r of equals x and height equals f of x into our formula for the area of these shells. So the important thing to note about this when we compare it to the last class is that now we have functions of x when we're revolving around the y-axis instead of functions of y. So if you remember back, the previous class, we had the integral, I'll call them different primes, I'll just call them a naught and b naught to differentiate them, of of pi, and then we had g of y squared dy. So what this allows us to do is that if we have some function that it's really hard to find the inverse of, it allows us to take these integrals without actually finding the inverse function in this case. So that's going to be one of the main reasons that we're going to be using this. So let's jump into an example. I have a picture of that right here. So the example, which they call the sine bowl in the book, I don't really know why, I guess it's a sine curve and it kind of looks like a bowl. So if we are doing this, we have a curve that kind of looks like this, and we are revolving it around the y-axis. So y, this is x, and we have f of x equals sine of x squared. Reason this is important, right? If we were trying to take the inverse of this, the cat wants to come in and say hi. Hi, Jerry. So right, if we were trying to take the inverse of sine of x squared, we would get a square root of a sine inverse, which is really hard to take the integral of, right? I don't know how to take that integral. However, you'll see in this that it ends up being not too bad to take the integral of this. The other important pieces of information from this picture is that we can see that our bounds of the integral are going to be from 0 to the square root of pi over 2. So setting up the integral, we have 0 to the square root of pi over 2 of 2 pi x. That's just the part that always is going to come from that, right? That is going to be our circumference function of these cylinders, and this is going to be multiplied by sine of x squared dx. Okay, so when you see this, your first thought should automatically be to do u substitution on this problem, right? We have a function inside of another function. We have this x squared inside of the sine of x, or instead of our sine function, and so we can use u substitution in order to make the x squared just a u, and then we can also use that to get rid of the x on the outside that we're multiplying the sine of x squared by. So in particular, right, you always want to pick u as your inside function, so u is going to be x squared. Taking derivatives, we're going to get du is equal to 2x dx, right? And this is great. So we have that this 2x dx here, and a dx, and a 2x right there, right? So we can take this 2x times dx and just substitute that back in for a du. The other thing that we always need to make sure to change are our integral bounds. So the first one is when x is 0. Well, if we square 0, we'll just get 0 still. So this implies that u is 0. And if we have x equals square root of pi over 2, we square this, we're just going to get that u is equal to pi over 2. Okay, so setting back up this integral, we now have the integral from 0 to pi over 2. The 2x dx goes away into the du, so we are just left with pi sine of u du, right? Much better than the square root of the inverse sine. Okay, so taking the integral of sine is going to be a negative cosine. It's the negative of what the derivative would be for sines and cosines. So this is equal to negative pi cosine of u, and this is going to be evaluated from 0 to pi over 2. Okay, so if you remember back to your unit circle, cosine of pi over 2 is 0, so we have negative pi cosine pi over 2. That is going to be 0, and then we subtract a negative, which leaves us with a positive pi cosine of 0, which is going to be 1. So we're just left with pi. And we'll say units cubed. Units cubed. So our final answer for the volume in this figure 6.45 up here is going to be pi units cubed. And this is a problem that we just wouldn't have been able to do using the shell method or the washer method. Okay, so the nice thing about this method is that the different things we talked about for the shell method, so revolving around different axes, using multiple curves, so the washer method, all of these extend to the shell method. So I will go through examples of all of these, but the process is going to be very similar to the previous section of 6.3. The big takeaway is you just always need to be thinking about how these cylinders are going to be looking. So specifically what your circumference or radii are and how those are going to change using different techniques. So the first extension of this that we're going to be talking about is going to be revolving around other axes. So specifically the x-axis we will talk about first. So just a quick picture of what this would look like if we have some graph with some function here. So this is our f of x. This is now our y value. This is now our x value. If we come up to the previous picture we were looking at, right, all of our cylinders are going to be parallel to the y-axis. So in this case, right, we can expect all of our cylinders to be parallel now to the x-axis. So in particular, if we're looking at a cylinder at this point right here, we are going to have something that looks like this. And there will be a nicer drawing in the picture I'm showing as well, but I think this gives a good idea of what the changes are. So now we can see that our height is going to be given by our function. So the height is now the x value of our function. So in particular, this is going to be g of y, where now our function is in terms of y instead of in terms of x. So this is the height, and our radius here is just going to be how far along we are. So this is going to be our specific y value that we're going to be looking at. So our radius is going to be y. And so what that means is that we can use the same method and get an integral from a to b, where these are now y values. A is going to be the lower y value, b will be the larger y value of 2 pi y g of y dy, where again, right, g of y is going to be this inverse function of f of x. So an example of this, which I have a picture of, is right here. So say we would like to take this function of x equals y squared plus 2, take whatever's in the first quadrant and rotate that around the x-axis. So what our function is going to look like is this. We're also interested in this line. This is going to be the shape that we were revolving around the x-axis. Now, you can think about it, and we would be able to use the shell method or the washer method on this one in particular, right? We could break it up into two different parts. We would have this part right here where our bottom function is just line x equals 0, and this part right here where we have the line and the quadratic, or the square root, excuse me. So we are able to do this using the washer method. However, in this case, if we do use the shell method, when we look at the lines going this way in it, we're always just going from the line x equals 0 to the curve that we were talking about. So this is really nice. It means we have to do less integrals, which is always a good thing to do. So in particular, let me pull up my notes right here, excuse me. So we have the function, this is going to be x equals y squared plus 2, which I guess is written right up there. And we have a y value of going from a equals 0 to b equals 2. So this line right here is going to be the line y equals 2. So what this means for our function, right, and you can see this here, is that our radius is going to be y. This will be in general true when we're just rotating around the x-axis, and our circumference is going to be 2 pi y, right? We just multiply the radius by 2 pi to get circumference, and then height is going to be this function value, now in terms of y instead of in terms of x. So combining this all together to get the area of the shells, we're just going to get 2 pi y times y squared plus 2. And now we can take integrals in order to get our volume of our solid of revolution. So in particular, we have that this is the integral from 0 to 2, because our top line is going to be y equals 2 of 2 pi y squared plus 2 dy. Right, one integral, we just have to solve this to get the volume instead of the two integrals we'd have to do otherwise. So this, if we distribute the 2 pi y through, is the integral from 0 to 2 pi y cubed plus 4 pi y. Integral of y cubed is 1/4 y to the 4th, so we're left with pi over 2 y to the 4th plus 2 pi y squared, right? The integral of y is going to be 1/2 y squared, so dy. This is an integral from 0 to 2. If we plug everything in, do all the math, we're going to get that this is equal to 16 pi as our final answer. So this shape up here has a volume of 16 pi. Just another reason the shell method is particularly useful. Even if we can use other methods, it will oftentimes be a lot easier to use the shell method. Okay. So the second extension we're going to be talking about is the shell washer method. Analogy doesn't work quite as well there. Shell washer method. This is basically when we now have two functions that we're looking at. And so if you think about it in terms of the cylinders, that means that our height is going to be different, right? We're going to have two different functions that we're going to be needing to subtract from each other in order to get our height. So going straight into a specific example, which I have right here. And so we're revolving around the y-axis again. If we think about one of these cylinders, just at, we'll say this x value right here, it's going to look something like this. So what this means, our radius is still going to be the same. Radius is the same. And it's still going to be our x value. However, the thing that's going to change in the cylinder is the height. So just in the general sense, if this top function was f of x and the bottom function was g of x, excuse me, the height now is just going to become the difference between f of x and g of x. So we need to not include going all the way down to the x-axis. So this is going to leave us with a formula of the integral from a to b of still 2 pi x, still have the same circumference of our cylinder, but now we have f of x minus g of x. Okay, so we can just take all of this, plug it into our equation that we have. I should say this is equal to our volume. And we can use this in order to find the volume again, right? So this is going to be kind of a ring shape, or it's going to be pointy on either end. So probably not a ring you would like to wear. Okay, just plugging everything in, we can see that our leftmost value here of x is going to be 1, right? We're interested in revolving around the y-axis, and we're using the shell method, which means we actually use x values. And our leftmost value is going to be 4. And we already have our functions in terms of y. One reason we might want to use the shell method on this rather than the just regular washer method is that you can't really take this x squared minus 6x plus 10 and figure out what a function in terms of y instead of in terms of x. You could do it, it would be very difficult. And so this is much easier since we don't have to take these inverse functions. So plugging everything in, we get that this is the integral from 1 to 4 of 2 pi x. And then we're just going to subtract our two functions in order to get our height. So we have x squared minus 6x plus 10, and we're going to subtract that. Oh, excuse me, sorry. This is kind of a confusing drawing. That is the bottom function. So the top function, 2 pi x, is going to be the one with the negative, right? It's a negative quadratic, so it makes sense to be going downwards. Negative x squared plus 4x plus 2. And we're going to subtract all of that from our bottom function, which is the x squared minus 6x plus 10. So if I hadn't caught my mistake there and I would have gone through with all of this, what would have happened is I would have always had a negative height. It's just the negative of what the actual height would be. So I would come out with a negative volume, which definitely does not make sense for these problems. We're looking at actual real shapes. They should have positive volume. So if you do get a negative volume, that's a good first place to check when you're using this washer method. Just make sure you don't have your top and bottom function flipped. Okay. So distributing this out, doing all of the integrals and stuff, we're going to get that this is equal to 2 pi x. We have a negative x squared and a negative x squared, so this is a negative 2x squared. We have a positive 4x and a positive 6x, right? The negative is going to distribute through, so plus 10x. And finally, we have 2 minus 10 or minus 8 dx. Again, from 1 to 4, you can multiply all of this out, right? We can expand out by the 2 pi x, multiply all that through in order to just get a polynomial, and then we can take an integral like we know how to do for polynomials. I unfortunately forgot to write down the solution to this integral on my note sheet. This is an example in the book though, so you can just look in the book if you'd like to figure out what the actual solution is. I don't want to go through the algebra of all of this right now though. I'd probably make a mistake. Okay, so the third and final difference that we're going to talk about, or different technique that we're going to be talking about, is going to be other axes. So like x equals 1 or y equals 14. So this is going to be revolving around other axes. So in the washer method, the big thing that changed is now we were talking about the height changing of our cylinders. In this case, we're going to be talking about our radius changing. So I'm actually going to go through an example where we have a couple of different things happening. So if I pull that up right here, we're going to go through this example where we're looking at the line y equals square root of x and revolving around the line x equals negative 1/2. So we have two different things happening. We're revolving around a new line. We're revolving around not just x equals 0 or the y-axis, but this shifted line. Furthermore, we're going to have to be using the shell method. So we're not going all of the way to the line x equals negative 1/2. We're just going from that line to 0. So if we draw out the shells that we're going to be looking at, and they're very clear in this picture, I would say. We have a shell, and it's going to go down a certain amount, and then in, and it's going to look like this. And this is going to go down. I guess not in right there. So just this. So corresponding over here, we have this, and then it comes out over here, and it's centered around the line x equals negative 1/2. So if we're looking for the radius is not just going to be the x value we're looking at, but it's actually going to be the x value plus 1/2, right? We have this little bit extra that we need to add to it in order to get to our center. So our radius is going to be x plus 1/2. Okay, again, our height is going to be using the washer method. So we are going to be using two different functions, and we're going to be subtracting them. In particular, our top function is y equals 1. So height, we have 1, and then we're subtracting out the square root of x. So that is going to be the height. So this means that the area of our shells is going to be 2 pi times the radius, so x plus 1/2, all times our height, so 1 minus the square root of x. Now you can see from this top part of the picture here, we're going to have an a value of 0 because that's the rightmost x value we care about, right? We're only going from 0. You can see in this picture down here that we have a hole, and we're going all the way to b equals 1. So taking all of this, plugging it into an integral, we get that this is the integral from 0 to 1 of 2 pi x plus 1/2 1 minus square root of x dx. And so to solve this integral, we can take the parentheses, FOIL them out. So this is the integral from 0 to 1. Still have this 2 pi here. The first term is going to be x. Outside term is negative x to the 3/2, right? I have an x to the 1/2 times x to the 1, leaves me with 3/2. The inside term is 1/2, so plus 1/2. And finally, I have a minus square root of x over 2 for the last term. And this is still dx. And so if we integrate this, we just get that this is 2 pi, integral of x is 1/2 x squared. Integral of negative x to the 3/5 is negative 2/5 x to the 5/2. We're taking these reciprocals. 1/2, integral of 1/2 is x. So this is x over 2. Sorry, 1/2 x. Integral of 1/2 is 1/2 x. And finally, square root of x is x to the 1/2. So the integral of the square root of x is 2/3 x to the 3/2. So we have 2/3 times 1/2 times x to the 3/2, and evaluated from 0 to 1. So if you plug all this in, do all of the algebra, this turns out to be 8 pi over 15. Okay. So the final thing that I'm going to talk about today, and something that's very important to be thinking about in these types of problems, if you're on a test or actually just in the real world trying to figure out the volumes of things, you won't necessarily know which of these methods that you want to use. So we're just going to talk for a little bit about which method is better in which situation. So we have a comparison picture of the methods. I need to be on this page. Comparison picture of the methods. And this is really nice too. This gives nice, good drawings of what the cylinders and washers look like and how they're going to be different. So the big takeaway from this is that sometimes you can only use the washer method. So if you think back to our first picture that we were talking about, let me just scroll up to that, way back at the beginning. The first method, the first picture we were talking about, we had x squared minus x cubed. It's just hard to take the inverse of that, right? And we get multiple different functions because we have the same function giving us different radii. So this in particular is going to occur if when you are taking the revolution around the y-axis, you have some function that's going to be hard to find the inverse of. That's going to be the first reason you would use the shell method. Another reason would be if you are already given the function and we are revolving around the x-axis now, and you're given the function in terms of y instead of in terms of x, then the shell method will work particularly well because the shell method is going to take the function in terms of y instead of in terms of x. And so you can see that with this bottom picture right here, where if we are revolving around the x-axis and we have our function in terms of y, we can just plug that straight into the shell method without actually worrying about the inverses. The second reason we might want to use the shell method versus the disk or washer method is that sometimes it's just easier. And this can be pretty clearly seen in which example? This example right here, where I talked about how you could use the shell method in this, right? We could just divide it into these two regions, use the shell method on both of those regions, you get two integrals, and you'd be able to figure it out that way. However, when we use the shell method, we were only doing one integral, right? And this was not a particularly hard integral. We had a y cubed and a y in it, which are in general not things that are hard to take the integrals of. If instead we were doing this using the shell method, we would have to take the inverse of the function x equals y squared plus 2, which would lead to a square root, which is a bit more difficult to take integrals of. We'd have to use u substitution because we'd have numbers inside of the square root. In this case, it would be completely doable. However, this method is going to be a lot easier than the other method. So it's a good idea to be very comfortable with both of these techniques, the shell method and the washer method, or the shell method. Yeah, I think it's a good idea to be comfortable with both of them, in particular because sometimes you're only going to be able to use one or the other. All right, thank you all for listening. This is a Friday lecture, so happy Friday. It's a Wednesday for me, but happy Friday to all.